Hello everyone. So we're going to be covering control systems. So this playlist and the vibrations playlist, they will go hand in hand because to do vibrations, a lot of time you're dealing with different types of controls, like by implementing a spring or a damper that is putting constraints on your system, and they're acting as type of controls. Well, they are controls. They're controls in your system, and you would use that to dictate the behavior of your system. For example, if you have a car going over a hill, you would use a spring and a damper which are your suspension, and those dictate how the movement of the wheels relates to the movement of the car. That is a type of control system. That's mostly mechanical system, but that is still controls systems. So these videos will go hand in hand together a lot, and I'm going to end up covering, say, a topic of controls, and I'll go over like the controls aspect of it, like how to analyze it from this point. But in vibrations, there will be a actual example of using control systems in vibrations, and we'll have some examples in this video to show you. So let's start off with, well, what is a control system? Well, a control system is, by definition, a series of interconnected components designed to impose a desired behavior on our physical environment. Again, the suspension is an example of your control system. When you're driving, the goal is not to have you feel those vibrations of the road. You want to be smooth. Well, the suspension, which is a spring damper system, which will be covered in vibrations mechanics series, how to analyze that, but those two components translate it so that you don't feel any movement whatsoever when you're driving. That is an example of a control system. Well, what are the components of a control system? They're the input, which is sent, the data is sent to a controller, which is sent to an actuator, which gives a process, which tells the computer to do some process or just perform some process, and you get an output. So the input is your desired behavior. A lot of the time it's your desired behavior. The controller is, it gets your behavior, and by that I mean it's so you have some sort of input and something going into your system, which we'll cover in a second. It's called an excitation. It's something that excites your system. It tells it to do a specific action, like the bumps. That is your input. There's two inputs. Your excitation, which is telling your computer what to actually do, and then what you actually want to do. So we'll say computer again, reads what is actually happening, and I was like, well, this isn't what I want to happen, and then the controller, which would be the computer, does something, puts in some commands, activates some systems to get the behavior you want from the one that you don't have. We'll do into more example of that later, but that's how a controller works. It takes your inciting incident, your excitation, will usually compare it to the value you want to happen, and then we'll try and get your desired output from your real world input. And then your actuator turns any energy you have, whether it's electrical energy, stored energy, mechanical energy, doesn't matter, turns the energy into a physical motion. No, it just turns into a physical motion. Like we'll do the cars, for example. Your input is your wheel moving along the ground. Your controller is the spring and damper, and what it's reading with air quotes, because it's a mechanical system, it's experiencing, which would be the input of your car or the wheel moving up and down. The actuator is also this spring and compressor, and that is turning any energy it has in it by the compression of the spring and dampers and turning that into the car being still because it's absorbing that energy. There's a lot more going on to that, and we'll be covering it more, of course, in the vibration series, but that is an example of a control system along this process. Oh, and then the process is just car moving. So it's a lot to take in, I understand, but this is just a basic, so it's a quick overview, and then we'll go into more depth on each individual part. So there are two types of control systems. An open system or an open loop control. Open system, also referred to as open loop control, and a closed system. Well, first we'll cover an open system. An open system is simply an input to a controller to an output. And an open loop is the easiest and simplest way to set up a control system. What it does is it takes some input, the controller does something to get your desired output, but it does not check if that desired output is actually the desired output you want. So an example of that would be like you're driving down the road and you have a speedometer. So the speedometer, for example, could tell you, oh, you're going 60, for example, 60 miles per hour down the road, or 60 kilometers, depending on whatever country you're watching this video from. But there's no way of reading if you're actually going 60 miles per hour, 60 kilometers per hour down the road. That's how an open system works. Gives you an input, but does not check if that output is the correct output. So there's a lot of errors, but it is the simplest one to set up. The other one is a closed loop control, or a feedback control. And this is the one that is used more often. It's also more complicated because it actually checks your output, sees if that's what you want. So it goes in an input, you get some controller, sends of course to your actuator to do your process, get some process, or I'll just say you get some output. And then the computer checks. Here you have some sensor, and the sensor checks if the output the system is giving you is the actual output you want. And this is important because now if your speedometer says you're going 60 miles per hour, with the closed loop control, the computer's actually checking if you're really going 60 miles per hour by checking the rotation of the tires, for example. And by knowing that, it says, oh, I'm actually going, say, 55 miles per hour. I need to speed up. Or I'm going 65 miles per hour. I need to slow down. And as a result, you have more control over what your system actually does. So we're going to cover the pros and cons now for each. So first, open loop control. Pros. It's cheap. You don't have to really do any extra programming. Create the math, create your system, plug it in. If it works, great. If it doesn't, well, it doesn't. But it's cheap. It's easy to make because you don't have to check anything. There's no extra sensors you have to put in to determine if what you want to happen is actually happening. It's just throw it in and go. It's like if you were to, for example, close your eyes and turn on and push a switch on a light. You don't know if it's what the button does. You just think the button will turn on the light, but you have no idea if it's connected whatsoever. You have no idea if it worked. You just simply close your eyes and push the button. That's an open loop system. Your eyes are closed. There's no way for you to know if the light actually turned on, but you push the button. So it should turn on, but you don't know. That is an example of an open loop control. Well, what are the cons to this? Well, it can be very, very inaccurate. If you don't know if the output you're getting is the correct output you want, then your system is unreliable. A car going down the freeway in open loop control, it says you're going 60, you could be going 100 miles an hour. The computer won't know. You won't know. I mean, you'll figure it out based off your relation to other cars, but you won't know, so it's very inaccurate. It also puts in a lot of uncertainties because you're not actually checking if what's going on is going on. This all comes back to, are you checking your output? Because if you're inaccurate uncertainties, yeah, they sound similar, but they're not, because by the inaccuracy is just your data, the uncertainties is you're not taking into account wind resistance, you're not taking into account friction of the ground, you're not taking into account the tread on your tires. All these things would play a factor that a closed loop control would analyze. So doesn't take into account uncertainties. So now let's do closed loop control. Start with the pros again. It's accurate. By doing a closed loop control, you check if your output is actually the output you want, and then the computer makes changes to fix it. For example, again with the car, if you wanted to go 60, the car reads you're actually going at 55, the computer will tell the engine to accelerate or inject more fuel to actually bring your speed up from 55 to 60. It can be better controlled because now that you're actually measuring your output, you can see if your output doesn't happen, you can see, okay, why does this not happen? Why am I not getting my desired output? And you can take measures to ensure that you end up getting your desired output by either putting in more components or adding more functions or changing your computer code. So what are the cons? Well, as you've probably guessed, with including all this extra labor and material, closed loop controls are more expensive. They take time. You have to put in a lot more work to get them to work, and work costs money. You need more components. Components cost money, and the price can add up. Another con is it's more complicated. It's no longer just put it together and hope it works. You're putting it together and you're checking it to make sure it works. And then if it doesn't work, you're adding more stuff to make sure that it works. So you're putting all these things on top of each other, and it gets complicated really, really quickly. I remember I had a code for one of my projects was just to turn the wheels and then check the speed of the car. Well, just doing that itself was 150 lines of code. Now, that's not a lot of code, but you still needed 150 lines just to simply check the speed, because we were going off of magnets, reed switches, and servo motors, and so we had to check those speeds to make sure we were getting the actual speed we wanted. So it gets pretty complicated, it gets pretty expensive pretty quickly. Also, you can overwhelm it. So feedback can overwhelm system. If you're not careful, you can be over-analyzing your system, and then your computer just can't keep up with the amount of data it's getting, and that can really slow down your process and make it very inefficient. And as a result, if you're getting overwhelming the system, that can actually really decrease the accuracy of it. So keep that in mind. A lot of the time though, you're going to go with a closed loop control system, like 99% of the time. I would even put it higher. I'd put it like 99.99% of the time, because you need to know if the output you're getting is actually the output you want. So our final thing we're going to do is the design steps. So how do you design a control system? Well, determine your components. Basically, what do you have? What components are you working with to do whatever job you have? Or You have a job. What components do you need to do that job? Next is quantify design requirements. Or basically, what's your objective? What's your goal? Now, this may seem like their 1 and 2 can be swapped depending on what you're doing. If you're starting from scratch, baseboard, you have nothing. You would start at step 2, or step 2 would become your step 1. You have to first determine, what do I want to do? And then you determine, okay, what components do I need? However, if you're fixing something, means you're later on in the design stage, you already have a prototype built. You look at, okay, what components do I have? And then I look at, okay, what do I want these components to do? In which case, it'd be ordered like this. So these can change, or I'll put it over here, change depending on phase of project. All right, step 3. Determine your system, and by that I mean determine your structure. And what that means is, are you using closed loop, or are you going to use open loop? Again, most of the time you're going to use closed loop. If you're kind of just dealing with a purely mechanical cycle, no electronics whatsoever, you're going to end up dealing with an open loop, and you're just going to have to design around that. Like most suspensions are open loops unless you get to really high-tech cars, because it's just a spring and a damper. It's a spring and a piston. It's just a purely mechanical system. Okay, next is you're actually going to build it. What are the parameters? What are you working under? So a parameter can be like, okay, I want to get it to, say, a car to 60 miles per hour. That's my parameter. That's how I'm going to operate this system. That's an example. So let's show these all in action. Quick example of this process. So 1, what do I want to do? Well, let's say first we want to design a speedometer. Design a speedometer. 2, what components will I need? Well, I'll need some type of computer. I'll need several computers, because I'll need to determine, okay, this is the speed I want to go to, this is the speed I'm actually having, this is my calculating function, so multiple computers. What type of system do I want? I'm going to go with closed loop, because I want to actually make sure I'm achieving my goal, because this is a computer type based calculation, so I can check my output. And so then now let's actually build it. Well, my process is going to be input my desired speed, then I want to have the value imputed in computer, do my speed calculation, whatever I need to do to get the vehicle actually to that speed. And then I get some speed. Now, since this is closed loop, I'm going to take that speed and I'm going to compare the output speed to my desired speed to see if they match. And if they don't match, then during this step here is when I would be calculating whatever variables I need to put into the computer to actually get up to that speed. So this is just a quick example of a control system basics. So you'll see shapes here like the circle, that type of stuff we'll go into in our Probably our third video or fourth video, because there's a lot of math involved in here, and so we want to cover that real quick before we actually get into the nitty-gritty details of control systems. But this here is just a quick basics on what control systems are. If you found the video helpful, like and subscribe for more content on. I'll be going over almost every single course in mechanical engineering. If you have any questions, please feel free to leave a comment and I'll answer when I can. Thank you very much and have a wonderful night.